Today we'll do combination of resistances. Now for resistances, we do for series combination and parallel combination. These are the basic one which we'll be doing first, and after that we'll go for the complex network. Let's take series combination. Suppose we have three resistances R1, R2, R3 connected in series across a source of EMF which gives the potential difference V. V1, V2, V3, these are the potential difference across the different resistances R1, R2 and R3. In series combination, it is the same current which will flow through all the resistances, not the same magnitude. It is the same current which will flow through all the resistances here. So whatever is the current drawn from the source, whatever current is going through R1, it is the same which is going through R2, which is same going through R3. So here we can write if V, which is the total potential difference, this will be V1 plus V2 plus V3. And V1 can be written as R1I, V2 R2I, and V3 R3I. So we can write R1 plus R2 plus R3I. This is V. Let's call this as equation number 1. Now we assume that let R be the equivalent resistance of the given network. Equivalent resistance will be the single resistance which will give the same result as produced by the given network of resistances. That means it will be drawing the same amount of current from the source as it will be derived by the given network there. So let capital R be the equivalent resistance. Therefore, V will be equals to Ri. This is the second one. And if you compare equation 1 and 2, so from equation 1 and 2, we get Ri as R1 plus R2 plus R3I. This I will get cancelled and R will be R1 plus R2 plus R3. So this is the expression for equivalent resistance for resistances joined in series combination. Now let's take the parallel combination. In parallel combination, if resistances are connected, then it will be the same potential difference across all the resistances. This you can take it in this way also. If one end of all the resistances are at one potential and other end is at other potential, then they are called to be in parallel combination. Because if one end is at one potential, other end is at other potential, obviously the potential difference across the 2 points will be same for all the resistances. So here we have R1, R2, R3 connected in parallel, and this is connected across a potential difference V. I1, I2, I3. These are the current through the resistances R1, R2 and R3. And here I is the current drawn from the source. So obviously I will be I1 plus I2 plus I3. And I1 we can write V by R1, I2 V by R2, I3 V by R3. So it is V 1 plus 1 by R1 plus 1 by R2 plus 1 by R3. This is the expression for I, and we call this as equation number 1. Again, let R be equivalent resistance. Therefore, I can be written as V by R. This is your second equation. Now, if you compare equation 1 and 2, so from equation 1 and 2, we have V by R as V 1 by R1, 1 by R2, 1 by R3. D, if you cancel, it is 1 by R, 1 by R1, 1 by R2, 1 by R3. This is the expression for equivalent resistance of the given network of resistances which are connected in parallel. This can be extended up to any number of resistances joined in parallel. Now, one thing you must remember, if we are calculating equivalent resistance, you are using this formula. Many times, if the value of R1, R2 and R3 which is given and we have to find equivalent resistance, we use this formula, we do the simplification of the terms on right side and we forget to take its reciprocal. Remember, whatever terms are there on right hand side, this is representing 1 by R. It is reciprocal of equivalent resistance. So if it is asked to find equivalent resistance, don't forget to take the reciprocal of the calculation done on right hand side so that you can get the equivalent resistance of the given network. And if it is only two resistances there, for two resistances, for solving numericals and other there, especially if you are solving an objective type and you want to do this quick calculation, you can use the formula R as R1 R2 by R1 plus R2. Okay. For two resistances which are connected in parallel. Let's try to solve some numericals based on the series or parallel combination of the resistances. Let's take the first one. Suppose the question is that a 10 ohm resistor is bent into the shape of a circle. What is the equivalent resistance across its two diametrically opposite points? So for this, let's assume that this is your resistance of 10 ohm which has been bent into the shape of a circle, and you have to find equivalent resistance across its diametrically opposite points like A and B. So you can take that this AB for this part, and the total resistance is 10 ohm, this will be 5 ohm, this will be 5 ohm, and between the points A and B, they are connected in parallel. So you have here 5 ohm, 5 ohm connected in parallel. So this will give you equivalent resistance as 2.5. Basically it is 5 by 2. You can use the formula R equals to R1 R2 divided by R1 plus R2. So that way if you take, it will be your 5 into 5 by 5 plus 5. So it is your 25 by 10 or 2.5. So this is the value of resistance across the points A and B. This is the second question. Suppose the resistances are connected as shown in the figure. This is a conducting wire and there are 4 resistances connected as shown here. We have to find equivalent resistance between the points A and B. So A is this point and B is any point on its circumference. Now since it is a conducting wire, obviously potential at all points of that will be same. Therefore, these 4 resistances which will has one end at one potential and other end at the other potential, that is the potential of the point B, they all will be in parallel. So we have 4 resistances connected in parallel. So equivalent resistance for this case will be equals to R by 4. That much only. Now let's take this as the third question. Again, it is a similar arrangement. we have to find equivalent resistance between the points A and B. So if you redraw it, suppose I pull the point A to this side. If you pull the point A, it is here A, this is your R. But for these three resistances, their one end is at this common point, which is the other end of the resistance which is connected, having one end at point A. So this is represented as these three resistances having one common point at this point, which is the other end of the resistance which is connected to the point A. So again, these are 3R, and the other end will be this one, so it is B. So for this case, it is your R, and here these are the three resistances connected in parallel. So this is R plus R by 3, giving you 4R by 3 as the equivalent resistance between the points A and B. Let's take fourth question. Here we have resistances connected as shown in the figure. This is a very simple question, but at least you will come to know how the resistances are connected and how we are reducing the net units there. Here you can see this 4 ohm and this 2 ohm. They are connected in series because if you consider, it will be the same current flowing through these two. So 4 ohm and 2 ohm, they are connected there in series. So obviously their equivalent resistance will be how much? It will be your 6 ohm. So now these two is represented by a single resistance of 6 ohm here. Now, how the two are connected? 3 and 6, they are in parallel. So as they are in parallel, their equivalent will be given by 3 into 6 divided by 3 plus 6. So it is your 18 by 9, and that is your 2 ohm. So that means this parallel combination can be represented by a resistance of 2 ohm. Again, we have 4 and 2 in series, giving you 6 ohm. That 6 ohm here will be in parallel with 3 ohm, which is already given. Again, this 3 and 6, they are in parallel. So they will give you again 2 ohm. So it will be 2 ohm. And ultimately this 4 and this will give you 6 ohm between the points A and B. So just by reducing the units, you can get the equivalent resistance between the desired points. Now in this question, you have to find what is the current drawn from the source, that is this 12-volt battery. If you look at the diagram, it is 20 ohm, 4 ohm connected there. This is 100 ohm, but there is a conducting wire connected here. So when the current will be drawn here, once it reaches point C, it has two paths to flow, one through this conducting wire and other through the resistance. As you know that if they are connected there in parallel, definitely no current will go through resistive path because the conducting wire will allow a path of very low resistance there. Or theoretically, it will be offering no resistance. So entire current will go through this. No current will be going through this 100 ohm. So the resistance of this circuit will be simply 20 plus 4, and that is 24. This is the resistance of the circuit. So therefore, no current as it is flowing through this 101, we can also assume that as if it is not connected there in the circuit. So the current will be equals to 12 by 24, and that is 0.5 ampere. This will be the current drawn from the source. Suppose you have to find equivalent resistance of this network. We have the resistances shown here. These are the conducting wires which is connected. So for this type of problem, what we do, we represent the points like this is suppose your C, this is your D, this is your E. This is the point A. Now, as it is connected by a conducting wire, so C and E are at same potential. So C and E, suppose we represent here to be at same potential. D and B will be at same potential because this is also connected by a conducting wire there. So it is your B and D connected. Now let's see. A and C are the points across which we have one resistance. So we have represented one resistance R here. Between C and D, C is here, D is here. So again we have one resistance. We have represented this. Between D and E, again E is here, D is here. We have represented this also. Between B and E, you have one resistance. So E is here, B is here. So you will have one resistance, so like this. So all these three are connected in parallel. So their equivalent will be given as your R by 3. This is your R. So equivalent resistance will be your 4R by 3 between the point and P. So for parallel combination, I have told you that you should use the definition if one end of all resistances is at one potential and other end is at other potential, then they are in parallel. Don't just use that one end is at one point and other end is at other point, then they are in parallel. Here their ends are not at the same points, but they are at same potential. So if you are using that previous definition that one end is at one point, other end is at other point, then they are in parallel, you will get confused and you will not be able to solve. But if you use potential concept, definitely you will be able to solve this. This is another type of question which you may come across. Here what will be given? You will be given a network of the resistances and you will be asked to find the value of R, that is this resistance, so that this network is independent of number of units. You have to find the value of R so that this network is independent of number of units. Like here, we have shown say 2 units. If suppose 3, 4, 5, 6 units are there, still it will give you the same value of equivalent resistance between the points A and B. Now, for solving this type of problem, what we do, if this is R, let's see from last unit. Here we have 4 and R connected in series. Current resistance will be 4 plus R. This is now in parallel with this 3 ohm. So equivalent of that will be given by 4 plus R into 3 divided by 4 plus R plus 3. So this will be the another resistance connected here. This is your 4 plus R. These two are in parallel. The parallel combination of these two, if you want that it should be independent of number of units, then it should give you the same value R which we are getting, because again here it will be the 4 and then it will be R. So that means this should give you the value R. So this will be equals to R. That means in place of this one, if I replace it by a resistor R, so again with the original network, if you see it is 4 and are in series connected in parallel with this 3R. So let's simplify this one. So this is 12 plus 3R divided by 7 plus R equals to R, or 12 plus 3R equals to 7R plus R square, or R square plus 4R minus 12 equals to 0. If you solve this, we can write this R square plus 6R minus 2R minus 12 0, or R if you take common, R plus 6, this is 2 common here, R plus 6 equals to 0. So you will get R plus 6 or R minus 2 equals to 0. If you take R plus 6, R cannot be equals to minus 6. So only possibility is there that R minus 2 is 0 or R equals to 2. So that will be the value of the resistance R, which will make this given network independent of number of units. This is question number 8. You have to find for the given network of resistances, which is basically infinite unit network. You have to find equivalent resistance and also the current drawn from the source. This is a 12 volt source connected to this network having internal resistance 0.5 ohm. And what is the current drawn by the circuit, that you have to find. So for solving this type of infinite unit network, what we do, we just try to remove one unit. And by removing one unit, our aim is to see whether after removing that unit, the given network is same as the original or not. That means this is the network. You have 1 ohm connected, then 1 ohm is connected across, then again 1 ohm across. Suppose I eliminate it from this part. That means I treat these two 1 ohm resistance as one unit. What you will see that whatever we have shown inside the dotted one, that means after removing one unit, whether it is exactly same as the given network or not. So you see that the original one was your 1 ohm connected, and then 1 ohm was connected across. Then again it was connected in series 1 ohm, and then 1 ohm was connected across. But our given network has 1 ohm connected across, and then it has 1 ohm and another 1 ohm connected there. So that means it is not exactly the same arrangement. So this choice is not correct one. So what we should do? We should go for another one and check that we get the exact distribution or not. Let's suppose we eliminate from this. So now you see, here you have 1 ohm across, 1 ohm across, and it is just repeated again. That means now whatever we have shown inside this dotted one, it is exactly same as the given network. Only difference will be that now it will have 1 unit less than the original one. But since it is of infinite unit network, removing 1 unit will not affect the resistance of the circuit. So that is the basic theory on which we try to derive this, or get the value of the unknown resistance or the equivalent resistance of the circuit. So let R be equivalent resistance of the network. So if I take this as the infinite unit network having 1 unit less, that means this distribution is now 1 ohm, 1 ohm, this is 1 ohm, and for this entire one, we can take the resistance as R, which we have assumed, that for infinite unit network, R is its equivalent resistance. So now how the two are connected? This R and 1 ohm, they are connected, they are in parallel, so that their equivalent will be 1 ohm, and this is now R by R plus 1. R into 1 divided by R plus 1. And this is the point. Like suppose if I call it as point A and B, this is between point A and B. How the two are connected, three are connected here? They all are connected in series. So it will be your R by R plus 1 plus 2. And now it is a single resistance. Now this single resistance between point A and B, we have already assumed that equivalent resistance is capital R. So this is equal to capital R. So R by R plus 1 plus 2 is equals to capital R. To simplify this, R plus 2R plus 2 equals to R square plus R, or R square minus 2R minus 2 equals to 0. If you try to solve this quadratic equation, the solution will be R equals to minus B plus minus B square minus 4AC divided by 2. So this will be equals to 2 plus minus root over, this is your 8 plus 4, that is 12 divided by 2. So it is your 2 plus minus 2 root over 3 by 2, or 1 plus minus root over 3 by 3. 2 we have already cancelled. So it means it has the two values possible. Either R is equals to root over 3 plus 1, or R equals to 1 minus root over 3. This is not possible because this will be less than 0. This is not possible. So only this is possible. So it will be 2.732. That much. So this is the equivalent resistance. Now, our aim was to find the current drawn from the circuit. So if this is the equivalent resistance of the given network, the total resistance of the circuit will have the resistance, this 0.5 also added to it. So for the circuit, R total will be equals to 2.732 plus 0.5 ohm, and that will be equals to 3.2 ohm. And if you want to find the current, then it will be your V by R total, and that is your 12 by 3.232, 3.72 ampere. So this will be the current drawn by this network from the source. You have been given a rod of cross-sectional area A and length L. But it's given that resistivity of this changes with distance as rho equals to alpha plus beta x. X will be the distance from one end. Suppose I take this as 0 and this as L. So it is varying like this. You have to find the resistance of this rod of length L. So you have to find a resistance of the rod of length So for solving this type of problem, what we do, we take an elementary section of this. Suppose we take an elementary section and this is suppose x0, this is x equals to L, and this elementary section is suppose it is at a distance x and its thickness is dx. Area of cross section we have assumed that it is A. So we know that R is rho L by A. So resistance of this elementary section, if I write, it will be your dr, and that will be equals to rho, it will be your dx by A. A is the area of cross section. So this is the resistance of this elementary section. But of course, rho here is given as alpha plus beta x. And then it is your dx. So this is your dr. If you have to find the total resistance of this rod, we'll just integrate this one to get the total resistance. So it will be equals to integral of this r dr, and this will be integration from 0 to L. So this will be your alpha x, beta x dx integral will be your beta x square by 2, 0 to L, and the whole term will be divided by E. So this is your alpha L, beta by 2 L square minus 0 by E. So this is your alpha L, beta L square by 2, and the entire term divided by A. If you take L outside, then it can be written as your L by A, alpha plus beta L by 2. So this will be the resistance of this rod of length L, whose resistivity is changing with distance given by the formula rho equals to alpha plus beta x. Alpha and beta are the constants.